Welcome to EE 555 discussion on Wednesday, April 9th, 2014.
Okay, good morning everybody. Let's get started today. Today we'll talk about some extra problems on reverse path forwarding and multicasting and IPv6. So, did you finish IPv6? Yes, right? Alright, so let's see. The first problem is related to what we saw first problem last time. So assume we have this topology here like the previous program. Consider the topology in figure 1. Suppose that all links have unit cost and that node E over here source. Using arrows like those shown in figure 1 indicate links over which packets will be forwarded using RPF and links over which packets will not be forwarded given that the node E is the source. Okay? So the evolution of RPF on that graph. The notation that we will use is this arrow and a small square over here, packet not forward beyond receiving router. So let's see. I will figure over here. F, E, D, N. Initially I'm gonna connect all. Okay, so let's work it together. Any ideas? We have this guy is the source. Okay, so we're gonna see how this is gonna evolve using RPF. So what is the first thing that happens in RPF? E broadcasts messages, a message to his neighbors. So at the beginning we have F, C, and D receiving the. So what happens after that? So first of all, do you agree that the first arrows will look like this? I mean, we will see if we can put, or we should put a square over here, meaning they will. But the first thing we need to do is show this flow. To remind you, we said that suppose all links have unit cost. Why we need the unit cost information? For finding the shortest path. Because we said, if you remember in RPF, a node forwards traffic that is coming from a link, the receiving node, to the source. You know, it forwards only if it belongs to the shortest path, right? With that said, what happens, let's say, in the case of F? Is EF or a shortest path link that connects F to E? It's got weight 1, so it is. Continue the forwarding. Okay, great. So C will do the same, directly connected to E, and D will do the same. So we know that those three arrows, they are not. Okay. Perfect. So let's take one after the other. So F will forward the packets to, and F is what? F's neighbors is not E, broadcast-wise, okay, the packets, so he will send the packets over here. Now, is FC the shortest path from C to the source? Why? It's EC, exactly. So the an ending point, right? We will not continue. I'm gonna draw it. Okay? So this means that at C, the message at F will not be broadcasted again. RPF. All right. What happens in the case of there is no other message broadcast by F. So in the case of from E, and this message should be forwarded to the neighbors of C, which is F. E is not included because B and A. Now, is C is going to forward we said that. So we have a message coming this way, a message coming this way, and nothing else. Now, what in each of the broadcasted messages of C, C broadcast a message, receives a message from C, it's not in the shortest path to source, so this stops here. Agree? In the case of A, in the case, do we have a shortest way to go to E? No, it's either 1, 2, 3 or 1, 2, 3. So 1, 2 is the shortest way to go to, so C sends a message to A and A will forward this message. So this arrow is not terminated. Now that's solved. And what about CB? B receives, it seems like here CB and the other way around they have the same weight. They have the same cost. So we need to break ties over here. Okay? We will assume that the shortest path passes from here. So in this case, we are assuming that we are not forwarding further. We say that the shortest path comes from here, so B will not forward the packet coming from C. All right, so we have taken care of all the broadcast messages of C. Great. We have also the case, we haven't seen D at all. We haven't seen B and A. D received the first initial transmission from E. It's the shortest path connecting D to E. He will forward the packet to his neighbors. We have a packet going here and a packet going here. So what's going to happen over here? G has no other neighbors, right? So he will not anybody else. Now, what is going to happen over here? DB, we said that this is the shortest path, so B will forward the packet. So B will forward the packet like this. And now let's see if transmissions received at C will be forwarded further. So this is the shortest path, so it's coming. So yes, it will be forwarded. Okay? And the same applies over here. So it will be forwarded where? Going to happen in the case of, what else do we have? We saw this guy. Excuse me? So A will receive a B, which is in the shortest path, so he will broadcast over here. Agree? B receives a message from A, which is not coming from the shortest path, so it stops. Transmission from B to A. Same, because this is not the shortest path. Is it? No, I wanted to show you this. B to A. Do you agree? Okay. What else do we have here? E to D. E to D, we say that D broadcasts. We covered all the transmissions, I think, right? It seems like. So the question asks for what? Let's just see. Indicate links over which packets will be forwarded using RPF and links over which packets will not be forwarded given that the source is... Sounds good? Okay. Now, problem number 2. That's an R over here. Let's see. Consider the topology shown in figure 4.46, which is coming from a textbook obviously, and suppose that each link has unit cost. Same scenario. Suppose as the center in a center-based multicast routing algorithm. Node, which node? Node C. Okay? Assuming that each router uses its least cost path to node C to send join messages to C, draw the resulting center-based routing tree. Is the resulting tree a minimum cost tree justified? Do you remember anything about that? So how this algorithm is going to evolve? We have a center-based multi, and C is chosen as the center. Okay? So can you help? Okay. So I'm going to first of all B F E D G. Okay. So now what is going to happen if we have C as a central node? Whoever wants to join will send. So the neighbors, we have C, we focus on C. And we say multicast routing, assuming that each attached router uses its least cost path to node C to send join messages. Each attached. So what's going to happen? A, what's the shortest path to C? This path. That path over here. What is the shortest path? This path. Right? C to E, this path, and C to F, this one. Do you agree? Alright. The rest. If you remember the messages, the way they propagate the join messages, then somebody D will send a message to his shortest path neighbor that belongs to the list, and the message will propagate. Like we will add this branch, let's say. Right? Because this is already attached to the minimum spanning tree. Or to the spanning tree. Yeah? Do you remember that? Over here. We said that we can break ties here if we have like, you know, equal cost. So let's assume that this from E. So in this case, we will add this branch over here, right? Then how about the D? Now we have do we have a spanning tree over here? Are we done? It seems like, because we have a tree that traverses the whole network graph, connects everybody, it's connected. We don't know if it's the minimum cost. How do you calculate the cost of a spanning tree? it connects C to F and C to E. Let's focus on the 1, 2, 3 nodes. Is it a minimum spanning tree? You have 3, you have C, and I'm telling you that a spanning tree is CF, CE. Is it MST? It is, right? So the way to calculate the MST, the cost, and claim it's a minimum or not is to sum the edge weights. To say, oh, okay, let me see, I can go from F to E faster than going up here. You know, what we're trying to do over here. So the cost of this MST will be the cost of 1, 2, 5, 6. So it will have cost 6. Now, over here we have another MST, which has cost 1, 2, 3, 4, 5, 6 as well. So we are good, but they're just not the same. All right, so each graph, of course, if you remember from algorithms, it has basically. It might be multiple. So it doesn't mean anything over here, okay? So justify your answer. We explained that, yes, it is MST, but different than the one in figure 446. Do you agree, guys? Okay. Any questions? What's an algorithm to find MST? Have you taken algorithm class? I think it's called Kruskal's algorithm, right? One greedy algorithm that I remember. Anyway, you can take a look in the algorithms book. The next problem we'll continue problem 3. Consider a network in which connected to 3 other nodes. In a single time step or time slot, a node can broadcast packets from its neighbors, duplicate the packets, all of its neighbors except to the node that sent the given packet. So that happens in a time slot. Receive all transmit broadcasts from the neighbors, duplicate and send them to all the neighbors. Step, neighboring nodes can receive, duplicate and so on. This repeat. Suppose that uncontrolled flooding is used to provide a network. At time step T, how many copies of the broadcast packet will be transmitted, assuming that during the time single broadcast packet is transmitted by the source node to its 3 neighbors. So I want you to visualize first and tell me how this network will look like. So we have considered a network in which nodes are connected to 3 other nodes. Draw one just small example. Can you, if ourselves to 4 nodes, connect all the possible pairs and we get this. So it doesn't mean we necessarily graph, but it's a good, example. So we have problem number 3. Assume the graph looks like the following. I'm just going to draw it because visualizing what's going to happen, okay? In general, you can solve this, mind the picture and not drawing anything. C, D. each node is connected to 3 other nodes. So we are good to go. And assume that the broadcast source is A. Okay? So how is the transmission going to continue over here? I'm drawing, I will just show who is getting each level in each slot. So at the beginning, we have A transmitting to C. Okay, that's T equals 1. At T equals 2, what happens? Why D? Because the other is exactly. So with this graph over here, we can see the transmission is going to continue. We exclude always the parent node of our at the new layer because we cannot broadcast to the source. So as you see, we have branches at the top level, 2 branches at the second level for each node, and then we will see how. So AC, you see AC, this has to be B and D. A, D, B, and C. This is T equals 2. The same will continue over here. So, message from B, what C is going to do? A and D. Let's continue the third level and then we can, what's going to happen. B is A and C. C, B, A, D. C, B. D, B, A, and D, C, A, and B. And this is at T equals 3. I'm going to show, keeps going like this. So now, how many messages, what is the question really asking? At time step T, how many copies of the broadcast packet will be transmitted, assuming that during time broadcast packet is transmitted by the source to its 3 neighbors. So a single copy transmitted 3 times over here. Time equals 2, have 3, 4, 5, 6. Time equals 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have over here, let's call it N, 3, at each level, and then we calculate the sum. N equals 6, right? 12. And I suspect N equals 24 in the next level because it's not. Make sense? So, of course, it's going to be a mess in the network because of the, obviously, in this particular example. All right, so what is the final answer over here? Any ideas? Sum those guys, right? I mean, we don't have to sum these guys. Let's see. No, the question asks, at time step, how many copies? At time step, to know this thing. So we want to, not the total, but you can calculate. So at time step, we transmit how much? And T equals, so let's make this as a function of t, this is how much. It has a 2 somewhere because every time it duplicates. So it's a second. So over here n is equal to n, no, it's t. Is there any 3 factor over here first of all? There is a 3 factor, right? So we need to multiply 3. If you want to multiply at t equals 1, 3, power of t minus 1. 2 to the power of t minus 1. Okay. Because over here it's going to be t equals 2, it's 2 times 2 equals 6, and then it's 4, 3 times 4, 12, and so on and so forth. All right. That's all, actually. Yeah, attempt T. Okay. Let's see the next one. Any questions here? So the next problem, and let's see how we do with time. Okay. It's asking for the following. We know that there is no network layer can be used to identify the hosts participating in a multicast group. We know that there is no network layer protocol that can be used to identify the hosts participating in a multicast group. How can multicast applications learn the identities of the hosts that are participating in a multicast group? There is no network layer protocol. What penalty we want to have and we don't have it? You seen the homework problems? There are some, maybe. I remember seeing something in the last problems of the homework set. Not the very last problem, maybe. I don't remember the number. It's okay. I mean, there is a problem that. So, question 7? Okay, so any ideas about that here?
The time is 19 o'clock.
If we keep sending. So what is the main task here we want to achieve? We want a network layer protocol, some protocol layer that can be used to identify the host participating in a... So how can a multicast application learn the identities of the hosts that are participating in the group? We want an application to learn the participating hosts. So, any ideas about that? What layer is going to be the protocol over here? There is no network layer, as we said. We need application layer logic to infer this functionality. And there are some protocols out there. I mean, you can build your own application that does that. So, think about it. How we can solve this thing? You have applications talking through multicast. And you want to let the other users that you exist, let's say. That's why everybody, if somebody, for example, at the application layer, you send messages periodically, echo message here, that's my ID, that type of thing. Who's going to receive? If it's a multicast message, The keyword here is multicast. If you send a multicast message in the group, then the recipients in the group will receive, and they will know exactly, they can keep a list of the participants. Do you agree? So the answer to this is we use multicast messages in order to a message that says, okay, I'm a member of this group, and the other participants will get the message, and we will do. Sounds good? Do you agree with that? Okay. So so the protocol be built at the application layer. For example, an application may periodically multi its identity to all other group members. In an application layer message. Oops. All right. So that's the problem. Now, you can design many algorithms that use this. Are we good with that? So now let's continue to another question. If you are fine with that, let's go to problem 5, which is IPv6. So in this particular case, we have a bunch. We're not going to cover all of them today, but I'll post the solutions. Okay? So the numbering is maintained over here because it's coming from. So we have the answers following the same numbering. Okay, 7, you go see the solution for 7. And so on and so forth. Okay, now let's see what the first question is. An organization is assigned an IPv6 block 1000:1234143/48. CIDR or cited address for the blocks in the first and the second subnets in this organization. Okay, we want to find the address for the blocks in subnets. Think about it and any ideas, guys? So you are saying it's going to be 4 zeros /64. Why 4? Perfect. And you from 0 though. But this is, I mean, we can at least explain that and assume that we start from 0. This is the subnets we get. If we assume that we start from 1, this is what we get. So very good, yeah. So the answers, let's write it down. So first of all, both subnets, the solutions here, but anyway, let's write this down. Both subnets use the given, first of all, global routing. What does this mean? It's the part of the address, the first 48 bits, right? global routing prefix. Each subnet adds how many bits? A 16 bits in hexadecimal. 4 letters anyway. Okay. Subnet identifier. All right. So, assuming anyway, we assume identifiers 1, 0, 0, 0, 1. What does this mean? Do you understand this notation? It means in hex format, right? They can also start from 0. But anyway, you choose one. Okay, so if we choose the first one, then what is the other? Then the subnet block is, we said we're going to keep the global routing prefix first of all, so it's going to look like 1, 2, 3, 4, 1, 2, 3, and then subnet 0, 0, 0, 1, and then 64. Why 64? Because we had 48 plus 16, right? Perfect. So the second subnet block will differ only in this digit over here. 2000 1, 2, 3, 4, 1, 4, 0, 0, 0, 2 slash 64. Okay. Let's see the next problem. Did you finish with that? Okay. The next question, the 8 we skip. Okay. You'll see the answer, but let's. So find the interface identifier of a node using IPv6 interface identifier. If its Ethernet address is F5, A9, 23, 12, 7, 8. Do you remember this case? Particular addressing, we use the MAC address to create the identity. Do you remember how we do the kind of expansion or padding in this case? 24, 24, and what else? It's not all ones, but it's something close to that. All ones? We'll see if it's all ones.
It's left, just heads up.
Thank you. Which case is the... He covered the case where we use the MAC address. Let me think. I see. In the thing I have, and I'm pretty sure that this is the right way, agrees with that, we use not ones, we use ones, all ones, and then a 0 at the end. So I don't remember if he was talking about another addressing mode that, which is, let me see, Yeah, we need, if you can see that says that, I don't think, this is in the notes. Do you remember if it's in the class notes or? Yeah, okay. So I need to repeat the lecture and see the particular addressing mode, guys, that we use here. We all ones, FF and then FE. Okay? But there is another addressing mode for MAC address. Let's see. So this is 9, question 9. Eh? Find the interface we said. So the change. Oh, did we talk about that? We didn't talk about that. I can show you a small example over here. So this is the initial address, MAC bits. Can you zoom in, please? Somebody in the control room? Anyway.
Yep. Zoom.
Thank you. So we have the Ethernet address, 48 bits, okay? And in order to convert that to the identifier, sorry, the interface interface is 64. Do you agree? So, sorry guys, is we change the the last bit anyway, from the first 8 bits, we change it to 0. That's the first operation we do. And as you saw, the local 0 ones. And the other is we take the first 8 bits, we place them here, then we add this FFFE, follow. Okay? That's the way to do the 8-bit MAC address. Do you agree? Okay, so we'll do the same. We change the 7th bit from 2 1. Oh, I'm sorry, guys. Right, from 0 to 1. Correct. We changed the 7. So in this particular case, the address was F5. Okay? So F5 will become 7. Very good. So we will have becomes F7. Insert 4 extra hexadecimal.
About at a time.
Sorry, yeah, I'm wrapping up now. The FFFE after the 6. So in this particular case, how much it becomes? F7, A9, F7, A9, 2, 3, FF, F1, 2, 7A, B2. Do you agree? Okay, guys. That's it. Thank you very much. And you can for questions if you have.
And this concludes EE 555 April 9th, 2014.